I have this stack of fluid dynamics papers here on one side of my desk, and on the other, a collection of beautiful nature photography.
An interesting combination.
It is, right. And today we're merging them. We're doing a deep dive into how a simple, a morning walk by a pond is actually a masterclass in physics.
The best kind of science.
Yeah.
The kind you can see with your own eyes, no lab required.
We are looking at the Kelvin wake pattern, specifically that V shape you see trailing behind a duck. It isn't just a random splash, is it?
Oh, not at all. It's a universal geometric constant. I mean, looking at these photos, you use the word engineered, and that's exactly how it feels.
Because it follows such a strict set of rules.
Exactly. It doesn't matter if it's a tiny duckling, a canoe, or even a huge ship. As long as the water is deep enough for the physics to work, that V shape is mathematically identical.
And it's so precise. I was looking at the data, and it's not like it's a range of angles. That chevron shape,
It's a V, yeah.
it has a total opening angle of almost exactly 39 degrees.
Right. To be super specific, each wake line is offset from the bird's path by 19.47 degrees. This is all worked out by Lord Kelvin back in the 19th century.
Thompson, yeah.
He was the one who realized this angle is completely independent of the object's size or speed.
Which is so counterintuitive. You'd think a giant ship would just push water in a totally different way than a small duck.
You would, but as long as they're moving at a relatively low speed, we're not talking about a planing speedboat here, the physics dictates that same 39-degree wedge every single time.
So the big question is why? Why that specific angle? How does the water know to do that?
It all comes down to interference. The bird is creating waves of all different lengths as it moves.
Okay.
But the visible arms of that V, those are just the very specific spots where all those different waves sync up and reinforce each other.
Constructive interference.
Exactly. But the real aha moment, at least for me in these papers, is the relationship between the speed of the waves and the speed of their energy.
Ah, this is the group velocity versus phase velocity idea. This is where it gets really cool.
It is. In deep water, the speed of an individual wave crest is actually faster than the speed of the energy packet that's creating it.
And it's a specific ratio, right?
A perfect 2-to-1 ratio. The group velocity moves at exactly half the speed of the individual waves, the phase velocity.
I was thinking about it like a race. The waves are like these sprinters running ahead, but the supply truck, with their water and food, the energy is jogging along at half their speed.
That's a fantastic analogy.
And because the runners can't survive without their supplies, they eventually they fizzle out. The waves literally outrun their own power source.
And that's why they can't break that 39-degree boundary. The energy just isn't there to support them any further out. It confines the wake to that perfect wedge.
And you can actually see the anatomy of it in these photos if you look closely. You see inside the V there are those curved ripples.
Yes, the ones that look a bit like rungs on a ladder.
What are those?
Those are called transverse waves. And then on the outer edges, the boundary isn't a solid line, It's made of these short, feathery ripples.
The divergent wavelets.
The divergent wavelets, angled at roughly 53 degrees to the path. It's so much order emerging from such a simple action.
It is. It's a reminder that even things that look simple on the surface often need a complex, optimized framework underneath to actually work.
That is true for physics, and it is definitely true for business.
Which is a perfect transition, actually. That idea of an optimized framework brings us to our sponsor, Embersilk.
Yes.
If you're out there trying to find some structure in your own chaos, you should check them out. Embersilk specializes in AI training, automation, and integration.
They help you figure out exactly where autonomous agents can make the biggest impact, whether that's for software development or just streamlining your own life.
So don't just make random splashes. Build a system. You can check out embersilk.com for your AI needs.
Nicely done.
Now, bringing it back to our duck for a second, there's one more little perspective shift from the source material that I absolutely love.
Is it about how the duck itself perceives the wake?
Yes. To the duck, those waves aren't moving away from it. They appear as stationary shockwaves. They travel with the bird.
So it's like a rigid structure that's just attached to it, moving along with it. A pure expression of linear theory in what we'd call an ideal fluid.
It really changes how you see things, doesn't it? You go for a walk, you see a duck on a pond, and you realize you're watching a live demonstration of geometry and velocity ratios.
The universe is incredibly orderly. You just have to know where to look. Physics isn't just in textbooks, it's happening right there.
Well, I'm certainly going to be paying more attention on my next walk. If you enjoyed this deep dive into nature's hidden geometry, please make sure you subscribe to the show.
And hey, leave us a 5-star review if you can. It really does help get the word out.
Thanks for tuning in to Intellectually Curious. Keep looking closer at the world around you.
You might just be surprised by what you find.